So today we're going to do section 4.4, which is look at the multiplication rule and the basics of that. Last time we talked about that combining them with that word or, when we had a single trial and we wanted one or the other, or both, but you're looking for finding that probability counted in such a way that each one's only counted once. So that formal rule that we just got through using on those last two was that you're adding those two probabilities and subtracting the ones that had both. Intuitive rule, if you know that you're getting ready to double count, you just count in such a way that you don't count anybody twice. And so it depends upon the type of way it's worded and how it's set up. Sometimes it's easier to do the intuitive rule. Sometimes you have to stick with that formal addition rule. All right, this section then, we're going to look at the basic multiplication rule is for finding the probability that A and B occur. That is the probability that event A occurs in a first trial and event B occurs in the second trial. And is going to be the key word we look for. So when we were doing the word or, it was one trial, you wanted one or the other, or both. In this one, you're saying the first time we do this, we get A. The second time, we get B, that we want both things to happen, one right after the other. The notation we're looking for then is that the probability that A and B occurs is that the probability that event A occurs in your first trial and event B occurs in your second trial. The sequence is important in here. So one is happening and followed by the other one happening. This might be that probability that you find people and that the next three people you talk to all live in Trenton. So probability the first one lives in Trenton, and the second one lives in Trenton, and the third one lives in Trenton would be one of the types of things you're looking for. Or the probability that you're going to find, you're going to select somebody that has a blue shirt, and then the next person has a black shirt, and the next person has a green shirt. So looking for something along that kind of line, where you're looking for those things that happen. And all three of them are going to, or two of them, whatever we're looking for, occurs. One of the ways that we can help ourselves in trying to figure out what's going on and what our options are is to look at a tree diagram. A tree diagram is a picture of the possible outcomes of a procedure. When we do these, we use the line segments emanating from one starting point. These diagrams are sometimes helpful in determining the number of possible outcomes in a sample space. For example, this figure summarizes the possible outcomes for a true-false question followed by a multiple-choice question. So trying to figure out if we got both of them right, obviously. So you've got your starting point. You're either going to answer that first question as true or false. From there, we're having a multiple choice that had the 5 options, A through E. So if you answered the true, you're going to have your A through E. If you answered false, you have A through E. So these are all the different combinations that you can have. Now, out of these, we know that only one of them is the right combination for the right answer. And so we can look at the tree diagram and recognize the probability that I'm going to get both of these questions right without having a clue what the answers are, just by purely guessing. We have a 1 in 10 chance that we get both those questions right. We had 2 options from the first one. We had 5 options on that second one. So notice that 2 times 5 gives me my 10 different combinations that we're going to be having. Kind of leading us towards that multiplication rule that we're getting ready to do. So the tree diagram kind of helps you organize what your different options are as you do things and how many different answers or different combinations you can get out of it. So now the conditional probability. This is an important principle that we need to have. The probability for the second event B should take into account the fact that the first event A has already occurred. Now, if you're looking at having a true-false question followed by this multiple-choice question, assuming that neither question is like a giveaway to the next answer, that it's not, by answering true that you now have picked which one you should pick from the A through E, that they're just 2 separate questions or 2 independent questions. Answering the first question true or false does not change what you would pick for A through E. So in this case, answering the first question right doesn't change whether you would answer the second question right. But if we were looking at having, if I was going to randomly pick people in the class and I wanted 2 people, if I've picked one person out of the class to be in my group, I've now changed the probability that the second person is randomly going to be picked because I've got a smaller pool of people to pick from. And so you have to take into account that that first thing's already happened. Does that make sense? Okay. The way we describe that or show that as the notation is that probability that B given A. That straight line up and down is saying that it's given. This represents the probability that event B occurs after it's assumed that event A has already occurred. So when you're seeing that straight line on there, that's saying that we're finding the probability that B happens given that A has already occurred. So if I was trying to find things in here, maybe it would be probability that I would pick Trevor given that Nathan's already been picked. So by picking the fact that we've already picked Nathan out of the group has changed the probability that Trevor is now going to get to be selected. If we have independent events, two events A and B are independent if the occurrence of one does not affect the probability of the occurrence of the other. My two questions that we had, true, false, A through E, were two independent events. Answering the first question right, especially if we have no clue what kind of questions are going on, answering that first one right was completely independent of whether or not you'd answer that second question right, especially if we're saying we were just randomly guessing as we were doing those. And so those would be independent events. Randomly picking people out of the class and trying to pick two people out of the class would not have been independent events because picking one of them changed the probability the other way. So when we talked about that one, I guess I should have said, and that was when we had that conditional probability. So when picking one of them changes the probability of the other, that's when you do have that conditional probability versus independent events. So independent events may be that if we were to flip a coin and roll a die, those would be two independent events. Whether I flip the coin and get a heads or a tails, not going to change what number I'm going to roll on my dice. And so those would be two different independent events. Dependent events then. Two events are dependent if the occurrence of one of them affects the probability of the occurrence of the other. This does not necessarily mean that one of the events is a cause of the other, though. If I was drawing cards out of my hand, once I've picked a card out, if I keep that card, then the probability of getting a second card has now changed. So if I'm drawing the cards and I pick an ace and I'm holding an ace in my hand, the probability that the second card's an ace is now different. Because now there's only 3 aces in the hand, and there's only 3 aces, and there's only 51 cards left in the hand, versus the original time had 4 aces out of the 52 cards. So you've changed that probability. So those would be two events that are dependent upon each other, that you change one of them. Which means as we're doing those, that we really have to pay attention to that conditional probability. Will be a piece of the things that we'll be looking at. So your formal multiplication rule. The probability that event A and B happens. First thing we do is find the probability that we get A. We're going to multiply it by the probability that we get B, given that A already has occurred. If these two things are independent, then if they are independent, then saying the probability that B occurs given A is just the same as finding the probability that B occurs. Flipping a coin, rolling a die. You're looking at two independent events. So the probability that flip a coin and you get a heads, and the probability you roll a die and you get a 1, those are going to be two independents. Rolling a 1, given that you already have a heads, doesn't matter if you roll a 1, given that you already had a tails, doesn't change. But if I was looking at drawing a card, and the probability that the first card was an ace and the second card was an ace, Then I have to change those probabilities. The probability I get an ace, given that I already have an ace, is going to be different. Questions there? But notice we're multiplying. When we were doing the, if we start back to that first one we were looking at where we're answering a question true, false, and answering a question with that multiple choice, probability that my first one was true, or probability my first one was right, I guess I should say, was 1/2. The probability my second one was right, given that the first one was right, was 1 out of 5, which given that the first one was right wasn't any different than just given that it was wrong. 1/2 times 1/5 gives me that probability of 1/10 that we already said we knew. There's only one right answer out of that combination of 10 different ways we could do it. I don't know if I've got a good example. Okay? Probability that I flip a coin to heads and I draw an ace. Are these independent or dependent events? Okay, these are two independent events, so go ahead and find that probability. That I get both of those. This one will be an easier one just to leave as a fraction. Okay, what's the probability that I flip a coin and get a heads? 1/2. Times the probability that I will get an ace, given that I already had a heads, which was just the same as saying the probability that I get an ace, was what? 4 out of 52, which is the same as 1 out of 13. So 1/2 times 1/13 gives a probability of 1/26. Questions there? What's the probability that I draw two aces? So, probability that I'm going to get an ace times the probability that I draw another ace, given that I am already holding an ace in my hand. So I'll give you a moment to think of that one. I'm actually going to stop you because I'm seeing things that are wrong as you guys are, as I'm giving you a moment to think about this one. What's the probability that I have an ace get the ace the first time? Okay, 4 out of 52, which is your 1 out of 13. What's the probability that the second card's an ace, given that I'm holding an ace in my hand? First of all, how many aces are there left? How many cards are left? Okay. So what is 13 times 51? Actually, it reduces, doesn't it? What's 51 divided by 3? Okay. And what's 13 times 17? Thanks. So your probability is 1 out of 221. What is that as a decimal? Three significant digits. So these zeros would not be important. They're just placeholders to help me get to these last three. So we are looking at the probability that you just randomly get two cards out of your hand or two cards out of the deck are both aces is less than 0.5%. Okay? Gosh, with the lottery going on, I really keep always thinking of this in the middle of this problem, these problems. I really should find the probability that you could win the lottery. Okay. Okay. We can look at that probability of how unlikely that you are to win the lottery. It's on the tickets. But you're looking at, because I'm trying to remember, because I don't play the lottery. How many, you have to pick 5 numbers and then the Powerball? So how many numbers are in each of those 5? Did anybody know anything? Only. Yeah. Okay. Great odds. So as you're looking at this one, your probability is really, really, really low because you're looking for that probability that you get the 5 numbers right. And that one we'll have to look a little differently because you would have, because you can't have those in the order. It doesn't really matter as much on those. And then your probability of getting that last Powerball, and I think there's even more numbers in the Powerball, aren't there? To where the chances of getting it is even lower. They'd make sure, and I know within like the last 5 years or less, that they increased the number of options that they had so that they could decrease your probability of winning. You know, we talked already in here about the expected outcome. Yeah. They make sure that they have that expected outcome where you lose money and they gain money, even though they have huge payouts on their lottery things. You know, you might as well just keep a hold of your money and have dollars left in your pocket. Yeah. Let's see, how do they word that? Tax on the poor, I think is how they call the lottery, for a reason. All right, applying the multiplication rule, starting with the fact that if we're wanting to find that 2 things are happening, as soon as you see the word and should trigger in your head, we're multiplying these probabilities together. So or meant you're adding. It's one or the other happens in one event. And is telling me that I want both of them to happen, and that's going to be multiplying. Notice if you're multiplying, you are making it the probability smaller, versus if you are adding values together, you were increasing that chance. If you're wanting to have that you get either a 1 or a 2, versus in one event you're getting that option, versus you have to get a 1 and a 2, then you're looking at 2 different things as you're doing it. So your and is telling you you're going to multiply. Next question you need to ask yourself is, are these independent or dependent events? If these 2 things are independent, then you just have to take the probability that A occurs times the probability that B occurs. On the other hand, if these 2 things are dependent events, that by finding one thing has happened, it changes the probability of the next. It's not a cause and effect relationship. Just because I draw an ace doesn't cause me to either draw an ace or not draw an ace the next time, but it changes the probability. And then if that's the case, then you have to take the probability that A occurs times the probability that B occurs given that A already has, because that's now changed your chances for B to happen. So if we look at number 18, first of all, when you look at number 18 on page 169, we need to fix the graph or the box that's at the very bottom. They left out some real important things, which was the different groups. If you have a used textbook, it's probably already been fixed for you. But if you're not, we need to make sure we have these in. So you need to put your different groups in here. That this first one's group O, the second one's group A, B, and then AB. Because I will ask you a couple questions about this problem too, and you need those groups. So looking at number 18. First of all, what this is saying is, use the data in the following table, which summarizes the blood groups and RH types for 100 subjects. These values may vary in different regions according to the ethnicity of the population. But these are our different groups of blood types. These are the different groups of them. This is the different types, where it's either RH positive or negative. Now, if we look at 18, it asks me if 3 of the 100 subjects are randomly selected, Find the probability that they are all group B and type Rh negative. First on A, assume the selections are made with replacement. If it's made with replacement, that's telling me I've picked somebody, I've looked at their blood type, I throw them back into the pool, and they might get picked again or they might not get picked again. Is that independent or dependent events then? Okay, these are now independent because I've thrown them back into the group and they can keep getting picked or not picked, so the probability of that person getting picked is still the same as what it was before. So this is looking at being independent events. So on part A, if these are independent, it's just going to take the probability that the first person is type B negative, the second person is B negative, and the third person is negative, B negative. So what's the probability that the first person is B negative? Okay, 2 out of the 100 people. So we are finding the probability that they are B negative times the probability that it's B negative times the probability that it's B negative. So each one of these is staying 2 out of 100. So we're looking at having 8 out of 1,000,000. When you put things like this in your calculator, if you get 8 times 10 to the negative 6th as an answer, your calculator will give you 8 negative 6 when you see some of these kind of things sometimes. That's telling you it's in scientific notation. Do not give me an answer using e's, because that's the calculator notation for this of saying it's 8 times 10 to the negative 6th. And I'm not sure if this one does that. I think it might be having enough decimals that it's okay. But I want to make sure we talked about that. Now, the next part saying, okay, so this one was with replacement. We picked a person, we threw them back. What if I want 3 different people? I want 3 out of my 100 to be able to look at. So now it's without replacement. If I'm doing this without replacement, are they independent or dependent events? Dependent, because now once I've pulled a person out and I've got them in my group, they're now no longer in the options of who I can change or who I can pick, so I've changed my possibilities. So first of all, we're going to say the probability that the first one is B negative times the probability that the next one's B negative, given that I already have one B negative, times the probability that I get another B negative, given that they're both B negative. Now, most of the time you won't write that out. This is just kind of what you're thinking. What's the probability that the first person's B negative? Okay, that didn't change. Still 2 out of 100. What's the probability the next person's B negative? Okay, 1 person out of the 100. What's the probability that the third person, after I've already, so oh wait, no, it's not 1 out of 100. It's 1 out of 99. What's the probability that the next person is also B negative? 0 out of the 98. Because now you're changing how many B negatives there are, and you're changing how many people are in our group. Obviously, if you multiply by 0, we're going to have what? I have no chance that out of that possible group of 100 that I could get a sample that had 3 B negatives in it. Because there weren't 3 B negative people in the group. Which common sense, without even having to do this, would have said, if you're having a group with 2 people that are B negative, what's the chances that you get 3 of them that are B negative? No chance. Questions there? Keep in mind as you're doing things, whether or not you have replacement, if it's with replacement or without replacement, because that does make a big difference in these problems. If it needs to have it, yeah. I want to come back to this one before I do anything else. So, if we're looking at a sample that is huge, let's say instead of having 100 people that we looked at a sample that had 1 million people. Obviously, we're going to have more than just 2 people that are RH or B negative. So if you are looking at having a sample that's 1 million, will pulling 1 person out of that make a big difference in the probability? No. And that's one of those things with the large numbers. If you're looking at having a sample that's 1 million, you don't have to say, okay, so we had, 10,000 out of the million were B negative, and so now we have to look at 9,999 out of, and then subtract 1 from 1 million, and being able to use that, because that probability is basically the same. Even if you only had a 5,000 in our sample, having 1,000 out of 5,000 is not much different than having 999 out of 4,999. The decimals, you're not going to see that change within stuff. So when you have really large numbers, you don't have to go through the whole let's subtract 1 off each one of them, because the probabilities change very small. The change in probability is very small to where it's not going to make a significant difference in your total probabilities. You multiply them together. Now, obviously, this one, even though 100 is not that small of a number, the fact that our numerator was very small made a huge difference within this problem. Because obviously, big difference between no chance and very slim chance. But you have to kind of weigh how much it changes your probabilities as you do things. All right. In the addition rule, the word or was going to be important when we say that probability of A or B. And when you saw the word or meant we wanted to add. On the other hand, so you're adding the probability that A and the probability of B occurring, where you're adding in such a way that every outcome is counted only once. On the other hand, in our multiplication rule, the word and in the probability that A and B suggest multiplication, where you're going to multiply the probability of A and the probability of B, but be sure that in the probability of event B takes into account that the previous occurrence has already happened for event A. So keeping in mind as you're doing these that you're looking at the other thing has already occurred. Questions there? I keep forgetting that I wanted to add in section 4.7. I have time to do that, but I didn't get my PowerPoint ready for it, so I haven't done it in the past. Oh, won't worry about it today. Let me just give you guys your homework. I wish I would have remembered that. I was wanting to get this because I wanted to talk about the combinations and permutations at some point in time. So it's one of those things that I've had left out of things, and one of these days I'll be able to put it in here. Not sure if it'll be this class.